couple of things that I just want to say to start with. We've got about 80 minutes now, and Cecilia's going to talk for about 40, and then like the first session, we'll have 35-40 minutes for discussion. And then after that, lunch will be provided, and lunch is going to take place just outside of the room here. Now, the point of the lunch, of course, in this particular session is that if you don't ask a question, you don't get any lunch. Okay, so remember that once we get into the second part of this session. The other thing I want to say is that I did notice a subtle difference in the name, the title of Cecilia's talk, as far as the session's concerned, and I fully agree with it that the original session was what physics is missing from climate sea ice models. And you'll notice the difference up there because Cecilia recognized that gravitational waves and Bose-Einstein condensation don't have an effect on sea ice models. So she's changed it to sea ice physics. Sorry, I'm just being stupid. Over to you.
I always feel free to permute my title. Anyway, yes, thank you very much for inviting me to speak, and I'm grateful to have this opportunity to talk, and I welcome the disagreements and questions because I think some of this is very controversial. Well, I'm also want to mention straight away that I'm talking about a lot of the work of people in this room, and I'm sorry if I don't give it full credit or correctly describe it. Please interrupt if I make some mistake. So I wanted to start by actually making a similar point to one that Dirk made, which is the difference between understanding and simulating. And really when we talk about adding complexity, I think we do it because we want a more faithful simulation. Probably not because we're seeking to understand the climate system better, or even the sea ice system better, although there's definitely some argument to be made that these don't totally separate. But if we just want to really understand the large-scale climate, probably all we really want is to represent the essential feedbacks and do them in a way that's relatively simple. But I'm really interested in also understanding and exploring how sea ice itself evolves, and that's where I think we need faithful sea ice simulations. So just very briefly, why I think we should care about the sea ice itself. There's a lot of things we could say, but I think the loss of sea ice in the Arctic is a major one, and the 50 or so % loss in sea ice concentration is extremely dramatic. But even more dramatic is the loss of multi-year ice and replacement with mostly first-year ice in the winter time, shown here as about a 60% change just since 1999. There were no data before that period. And I think the impacts of this loss of sea ice is tremendous for humans. Obviously, it allows opportunities like shipping, but it also causes dangerous waves that have contributed to eroding permafrost, and then the combination of eroding permafrost and waves has caused more erosion that has damaged infrastructure in native communities. And also I'm concerned about the disagreement among models when we try to project into the future, and I don't know that this is entirely due to lack of complexity. In fact, I really doubt it. I think the bigger issue here is that these models are forced very differently from the atmosphere and ocean, and that they also have some errors in them, and probably some of those errors lead to changes or influence the feedbacks that set the sensitivity. But one of the biggest reasons I'm really interested in model complexity now is because I want to predict the short term, the day to seasonal sea ice. And I think we really care about where the sea ice is and how it evolves and what its features of lead orientation, for example, might be, because that could affect the way we use the sea ice. I participated in a summer school in 2007. I think a number of you in the room were there. And it was in July, and a month or two later, the sea ice looked like this, right? And I don't recall any of us discussing at that summer school that it would be a record low year, or even a, interesting year. And it was really clear already. Evidence was there to be seen. So I think predicting sea ice is important. It has potential value for humans, but it's also something we can do. And I think we have a lot of room to get better at it. Just a quick picture of what predicting sea ice might look like. This is predicting the volume, and it's the total Arctic volume. It would look different depending on the location, but it's fairly representative of what controls the predictability. And there's a couple of different possibilities. It could be driven by climate forcing, right? It could be driven by the initial condition, and that initial condition could be a factor for both how close it is to the initial state, and therefore, let's see a pointer, how much time it will take before. Sir? A stick.
There's a very big stick in there.
This one?
Yep.
Yeah.
All right. So I think this picture, this cartoon up here tries to capture kind of what I'm talking about. That you expect some kind of overarching background trend, that red distribution. And then if we know what our state is at one point in time, how long does it take for the mean of our state to return to that mean of the background red downward trend? And how much does the downward trend change over time, as well as the spread grows so that the distributions are no longer distinctive? And this figure tries to capture all of those sources of information in a measure of information. And one thing we see here is what is initially, we have a lot of information from knowing the initial point and knowing the initial spread. And that it rapidly declines. After a couple of years, it's about the background level of just a red noise signal. So no information. But then what grows is the forced response. So what this basically says is that our initial condition gives us information for 2 to 3 years, and that amazingly the climate signal starts to become observable or measurable as a driver in a couple of years. So that's really impressive in terms of how fast it is that transition moves from one to the other, and that there's a very little time where there's a gap, where there's no information. So that gives us a good reason, I think, to simulate both the initial decline in initial conditions and also the forced signal. I've also recently become very interested in the role of very short-term climate signals or weather signals. For example, just last summer, a big storm hit in August, and the sea ice really fell apart. I'm looking at the amount of kind of black here increased dramatically. So the concentration kind of within the ice cover, I was told to be aware, and I did not cause this. Hang on, okay. So you see the concentrations really dramatically changed. The edge, however, isn't. And in this case, the extent changed very little, but the concentration changed dramatically. So kind of the way we simulate these kinds of loss events has big implications for how we might use the sea ice and prediction for, say, shipping in the region. So currently, the state of the art for prediction isn't at the level where it could be. And there are two kinds of simulations here shown. One are totally operational, so these are initialized with the real conditions in the Arctic, and then they're run forward, and this is a measure of the root mean square error in the prediction after 2 months. And so the level of no skill is shown here, which would be just an estimate from damped persistence of the anomaly and at the start. And it shows that basically we're almost at that level of no skill. But the potential, what is known as a perfect model estimate, where we take away the error in the model and the error in the initial condition in an idealized experiment, and we ask how well could we predict if we didn't have model errors in initial conditions. And you can see it's a much smaller. So this tells me that we have a big gap and a potential to improve our models for the prediction problem. So that's my motivation now. I want to talk about what models kind of state at the current state look like. And this is a schematic I made years ago that tries to illustrate the ice thickness distribution and the fact that models with an ice thickness distribution generally have a full flux budget for each category. They generally treat a melt pond parameterization of some sort for each category. They have temperature profile, maybe salinity in each category. And then among the categories, there's exchange due to deformation. So this tries to illustrate the ice thickness distribution, a little bit about thermodynamics. It doesn't really illustrate dynamics, but this whole ice grid is moving as well. So that's kind of the three ways we often separate sea ice into maybe three modules or types of processes. And I thought it would be interesting to show you a little history of sea ice models, just in terms of dynamics, the ice thickness distribution, and thermodynamics. CMEP2 was about 15 years ago. So these were 12 models, and I broke them down by complexity, with highest complexity at the top and the least at the bottom. So the majority of models 15 years ago that submitted their simulations to the intercomparison project had no sea ice dynamics. The majority had just two levels, so open water and ice, so no thickness distribution, no multiple categories in the thickness distribution. And among the thermodynamic possibilities, going from a zero layer to as best we can do with multi-layer physics at this kind of climate scale, the majority had zero layer, so no heat capacity, and therefore, no layer in the ice, so therefore a zero heat capacity effectively. Then, state of the art, just 7 years ago or so, well, maybe 10, I guess, if I add the time since the last IPCC too. But this would be the second to the last IPCC intercomparison project. I think it's really remarkable how we shifted in dynamics. Models really got it, that they need to have sea ice dynamics. And they didn't change dramatically in the ice thickness distribution. A few evolved to having an ice thickness distribution, and a few evolved to having some kind of multi-layer physics, but all of them have the fixed salinity approximation like Maked and Untersteiner did. Then, now, the most recent, this would still be about 7 years ago or so, 5 years ago or so, given the lag of IPCC. Now we're at a situation where all of the models essentially have dynamics. A few more have ice thickness distribution, and a few more have the more sophisticated thermodynamics. So I guess if I try to summarize this, I would say we got that dynamics is key. We haven't really, as a community, embraced the ice thickness distribution wholeheartedly, and we are really not sure at all what to do with thermodynamics. Well, sea ice is complicated, and this picture kind of strikes fear in my heart when I think about trying to simulate this system. I started modeling sea ice before I ever saw anything like this, which is probably a good thing. And a lot of pictures have a lot of different views. But one thing we see, melt ponds are a major issue, and flows are a major issue, and those will be features of my talk today. But dynamics, I'll try to illustrate here with a series of satellite images. This is complicated stuff, right? It has these giant length scales of cracks that are aligned, and well, a lot of different things happening at once. Large flows, small flows, and this is in early spring. I think this picture is useful from Danny that I stole, showing that these linear features and organized angles within the deformation of the ice appear at all length scales. And they matter because once there's a linear lead, the compressive strength differs if you push on the ice, if there's stress on the ice perpendicular or parallel to the lead. And so that changes the evolution of the lead itself and the motion field. So this is sometimes called anisotropy in the ice. And the question is, do we need to simulate it? Well, most models still use something like a viscous plastic material assumption and a continuum hypothesis. So can we do that and still, and at the same time, treat this anisotropy? And the answer is yes, there has been some really nice work on this. But first, just can we actually just accomplish it by increasing the resolution? And so this is what a grid cell of flows might look like, and if we increase the resolution, is this going to solve the problem? And it does somewhat, but I think it is highly debatable whether it's right. This is a simulation of a multi-scale model, so it has an unstructured grid, and the finest resolution is 4.5 kilometers, and it uses EVP dynamics without anisotropy in any fashion. So they just basically cranked up the resolution to see if they can capture these kinds of features, and you can see they're there, but you might argue they're not exactly like they were in the satellite, and maybe in important ways. So another pieces of slides that I've swiped from Danny, where he did his group work on trying to add this kind of anisotropy to the EVP model. So the idea being that we can't necessarily always afford to simulate flows and the granular structures at the resolution that they need to be in reality, such as you would see in a discrete element model at left. But if we look at a model like that and explore it and learn from it, can we develop a method in our larger scale grid model that treats the flows here shown as diamonds such that we can represent some of the anisotropy? And all of this comes into the momentum equation in the ice interaction term, the so-called ice-ice force here. And their group has done a lot to do this, and it has been very successful. And I think it's a really good situation where we can still run practical levels of grid cells at 50, 100 kilometers and see the kinds of behaviors that we aim to do with the very fine resolution or the discrete element model. So another thing that has come up recently is to try to treat the fast ice, which is right along the coastline here in this figure from satellite, which these models at like 100 kilometer resolution or even a 10 kilometer resolution don't necessarily faithfully treat. And one reason is they generally think of the sea ice as levitating above the ocean. They're not embedded in the ocean. And some studies have, or some groups have tried to take into account things like the keels dragging in the sediments and the effect of that on sort of stalling the ice in that region, which I think is a really cool new addition. So that's all I wanted to say about dynamics. Given that I only have 40 minutes, I really can't do much more justice to this topic, and besides, there are many more in the room who know much more about it than I do. And I'm going to speak a little bit on ice thermodynamics now and the growth process. And how I think we have not really attempted this at the level I think we should. So the two branches of this diagram say that once the ocean temperature should drop below freezing in a situation of ice growth in open water. And there are two possibilities. In a calm ocean, we expect frazzle ice to accumulate into grease, and the grease ice to accumulate into nihilus, and so forth. Or the other route is to create pancakes if the frazzle ice is in waves to accumulate through that mechanical driving. And the look of the ice is very different, and the albedo is very different. Right? The albedo stays low here for a lot longer, probably. And also you see the wind effect kind of accumulating the higher thickness ice off to one side, collecting it. So there has been some effort to treat these two limits. Some of the issues that are important for grease ice I've listed here. I think I'll skip it in the interest of time, but most of these things I already mentioned. The model that I'm thinking of that has treated grease ice recently is another one. I think you're in the room, right? Yeah, hi. Volkunsky et al., 2015. And this nice schematic they have where they treat the fact that the grease ice is collecting downwind in the lead. One thing I would point out that the lead box here is still a uniform temperature and salinity, and I think that's practical, probably around 5 meters deep or so, and that this, in fact, is a region where you'd expect, because of heat loss out the top, strong convection, and something that I think there is more room to consider how we should parameterize that convection and or resolve it. And so from there I wanted to mention a couple of other strategies that I think are interesting, that is to explore how to simulate that kind of turbulence using, say, a large eddy simulation model where you just look at a very small region and try to attempt to understand the turbulence and the growth interaction. And it has been done, but what I think hasn't been done, and I'd like to see us consider as a community, is trying to embed this kind of model into a global climate model. And this has become kind of all the rage in cloud modeling right now. And there's a new paper by Tapio Schneider where he describes this kind of approach where you would embed a cloud resolving model into a global climate model. And a three-dimensional one, probably you could only afford a very small region. And then the interaction of the two, so that that large-scale climate model would affect transport of moisture into the grid cell, and then the convection actually resolved here could be sort of exported out in terms of influencing the way convection is treated elsewhere. And they're talking about trying to do this with machine learning type of methods, but hasn't quite been implemented yet, and I think it's something that shows some promise, and I think we could use this kind of technique to explore adding complexity to sea ice models, where we could put large eddy simulation models in the leads and potentially in the atmospheric boundary layer as well. Or we could do something like this, but with the discrete element models for flow and potentially for anisotropy studies as well. So I want to change topic slightly to drill down even further to the thermodynamics of the actual ice itself, and the excellent work that has been done recently on this topic. I'll mention very briefly to try to really account for the pore structure in the sea ice and its influence on how it evolves. So these tomography pictures show how very little, and by the way, this is pore, not ice, solid fraction. Phi is used for both, unfortunately, and they're just one minus each other. So here, very small values at the pore fraction look very connected, and indeed that's the case that when we look at the amount of pore volume in a thin section, few percent, something like 5% or so, leads to connectivity and brine exchange. I took this picture with Pat, actually, remember? And you can also see it's not all vertical. There's plenty of transport in the horizontal, which is another thing that concerns me late at night. The two equations that Danny showed earlier, just to use his two equations, have been implemented in models at this very large scale. And he mentioned also that the approach by that Wickett and Untersteiner was to set the salt balance tendency equal to 0 so that the salinity in the ice is fixed, and also to ignore any transport in the brine channels of heat and salinity, obviously, since it's gone from this side of the equation, but it's also gone from the heat balance equation. That's how Wickett and Untersteiner solved this. Years ago, 1971, on the UW mainframe, I have, I think, some of the punch cards from that experiment in my office. I use them for notes. The students don't know what they are. Anyway, so very, I think, elegant solution, and one that can be very easily used in climate models today, and yet it isn't as much as it could be. Then the more recent approach of Turner et al. Was to actually go one step further and simulate the salinity balance equation as well. And the way they tried to deal with this problem was to cast it into a one-dimensional parameterization, where the downwelling flux is accomplished in channels. So larger, envisioned as a larger flow channel downward, and then in the mushy layer of the ice, the flow is upward. So definitely a parameterization, one that could be debated, and probably a different interpretation could be and should be explored, and I think that's something we should look forward to seeing as a new evolution in climate models. This has another attractive potential, which is it gives us the ability to add algae and the cycling of nutrients into the ice. As we're cycling seawater in that influences the salinity, we can throw in other tracers that give us a new capability. I should stop at 12:20. Is that right, Vernon? Yeah. 12:20? Yeah. So I think I won't say too much about melt ponds other than to say they're hard. We're doing great things with them. I think really nice work has been done by Daniela here, and I was talking to Elizabeth earlier how her method differs, and it's quite similar. It's slightly different in terms of where you decide the water lies, but the geometry of the problem, but the basic idea that we're already considering how the pore structure allows for drainage, and there's some efforts to look at pond refreezing. But what I really wanted to talk about was flows, and yeah, I think these features in the ice that are these large-scale filaments that are occurring at the ice edge are an indication of how large-scale the influence of waves are in the ice. Obviously, there's eddies in the ocean that are also incorporated in creating these filaments. And I haven't heard a lot about them, so I'm curious, as a community, if others will correct me that this has been explored. But the picture here of the Antarctic Peninsula in this is early spring, so early enough though, late enough that the ice edge is already retreating. So this is melt season, this isn't frazzle, this is flows. And the waves suggest that there's a lot of organization going on at the ice edge that we are not modeling yet. And if you look closely, you can see really interesting banded structures. I don't see flows there at all, but the scale here is 20 miles, so it's quite large. I'm guessing this is just, you see flows, and then as you get to the left, flows are so small because they've been broken so severely in the waves that it starts to look like it's just smooth, but I'm assuming those are small-scale flows. Having never spent much time in a ship in the ice, I think I do not know for sure, but this interesting picture from a commercial flight of a similar kind of filamented structures in the ice. If you look closely, there are dots, which suggest flows. So how do we model this? It's waves moving through ice, definitely a challenge. And I won't talk about the wave part, but I will mention how we can treat the flows. And this is new work by Chris Horvat, who was here until a couple days ago, visiting, and suggested we could go one step further with the ice thickness distribution and treat it as a joint distribution of flows and thickness simultaneously. So the equation that describes the distribution is shown. It has very similar structure to the ice thickness distribution equation itself, but the treatment of braking is a key. And that distribution, the joint distribution, if you integrate it in either radius, you can get the ITD, the thickness distribution, or if you integrate it in thickness, you can get just the flow size distribution. This has been implemented recently by Letty Roach, who's here, and in this joint way, so simultaneous two-dimensional distribution. And she's going to show a poster today where she will demonstrate that she has already managed to run this model to an equilibrium to achieve a distribution with smaller flows at the edge, as you would expect, and they definitely get very small at the edge, just where they really matter. They really contribute to ice albedo feedback at the ice edge. And the controlling features of this distribution is shown on the right, which lateral growth is a very important one, but I think one that we didn't anticipate in advance and turned out to be extremely important is the flow merging. So removing flows of the thinnest category as they merge with their neighbors and become bigger flows turns out to be an extremely important and challenging aspect of the simulation. So the last topic I want to talk about is data assimilation, which seems like a little departure from what I have so far, because this doesn't involve complexity in the sea ice physics, but it certainly involves complexity, as I've learned all too well. So my group is working on this with the sea ice 5 model, and we've done this in the framework of CESM, so it's a fully coupled or system model. And again, that's schematic, so we're trying to actually assimilate observations into this model that doesn't look, the one-to-one observation to model variables is not simple. So instead of actually being able to, say, assimilate an ice thickness distribution, there just aren't enough observations of it. What we assimilate instead is an aggregate, like pixel average from satellite sea ice concentration. Well, that corresponds to the total, the sum of all of the concentration in the categories. So when you assimilate an observation like this, you need to distribute it among the distribution. And things that we have tried to assimilate are concentration, thickness, and first-year, multi-year ice concentration. And I just will say quickly that what I've learned is in idealized settings, again, these are so-called perfect models, so we eliminate the error in the model and ask just if we knew the observation, because we're synthetically observing the sea ice concentration, we can reduce an error almost completely. The light pink here is less than 2%. So even though there's this complication of the model having a subgrid scale distribution of concentration among the categories, we've been able to solve that problem. It's challenging but doable. Works really well. But what doesn't work well is when we just assimilate sea ice concentration, it doesn't actually improve the bias in thickness. So if we start out with a bias in the thickness that's on the order of 1 meter or so in the ice without doing any data assimilation, if we only assimilate sea ice concentration, it really doesn't help. So this was a good lesson to me, because almost all data assimilation today is just sea ice concentration for good reason. We don't have great observations of thickness. But if we just use our idealized thickness, we can essentially eliminate the bias. So that's good news, because we may someday have reliable long-term observations. And we can use SMOS and cryostat today and definitely do better for the last 5 years or so during the limited time of year when those data are available. But one thing I learned from this was that if we assimilate multi-year first-year ice faction, we actually reduce the error quite a lot. It's not as good, but a very promising result. So why would we do all this? Well, obviously, it's a little cheating because we don't have observations of the future, so when we simulate the future, we cannot take advantage of data assimilation, but it very much helps us nail down the initial conditions for a forecast. But there's something else it does that I think is largely, didn't realize this was animated, isn't well recognized, and that is you can use data assimilation to actually identify the best model parameters. And this is a little schematic of what data assimilation looks like. Here's the assimilation box. You run your model here, your sea ice model, or maybe even Earth system model, and out comes something that you want to adjust to an observation. So you put in your state vector here, a bunch of variables, and then you can also put in model parameters. And then when you combine that with observations, you can optimally identify the best choice of model parameters. And repeating that cycle again and again, you can see like what time of year the best model parameters are available. So I think this is a promising way to actually improve our models. It's a tuning, but sometimes we have to tune, right? So just one last reminder, I think my other kind of big idea, I think, is to try out these kinds of embedding techniques that I mentioned before. So data assimilation and these embedding techniques are, I think, things we should explore as a community. So in summary, there's a lot of new promising physics, much more than I was able to cover. One question I'd like to ask, though, is, our model is just too modular. Have we kind of been trapped in this idea of thinking that there's ice thickness distribution, there's thermodynamics, and there's dynamics? And should these things be interacting much more closely? And I think we're getting closer to that when we think about how flows actually influence the ice rheology. So shouldn't we be thinking more carefully about how flows, ice thickness distribution, and dynamics, ponds, all these things interact? And it's attractive to treat a system as a bunch of modules because you can swap them in and out. But the downside is you miss the interactions among them. So I think there's a lot of opportunity with new techniques like data assimilation and embedding, or just using sequentially these very high-level models like digital elevation models and large eddy simulation models. And then finally, I've not heard about these filaments before, and I think it's probably my ignorance, but potentially it's a new area that needs exploring. And I'm sure there are many others.